Hello, chemistry students. By now you should have watched the video where I did the two reactions in my chemistry kitchen. And now we're coming back to the packet so that we can explore a little bit more what endothermic and exothermic means. In the last video, we talked about what it meant for phase changes, and now we're going to apply these classifications to chemical reactions. And so I filled out the data table already here. Reaction 1, we obviously had a temperature that was decreasing as the reaction took place. And in reaction 2 with the steel wool, our temperature went up. And so my first question is, which reaction is giving off heat, or which one is releasing energy? And remember, you always have to think about it in terms of system versus surroundings. So it's the system that is releasing energy or giving off energy into the surroundings, and it is the system that would be absorbing energy from the surroundings. So you always have to think of it in terms of system and surroundings. So letter A is asking which reaction is giving off heat. Well, if a reaction is giving off heat, then that would register as an increase in temperature by our thermometer. And the one that was doing that is reaction 2. So reaction 2 was giving off or releasing energy. And since reaction 2 was releasing energy, that would mean that reaction 1 was absorbing energy. And again, it was the molecules that were participating in the reaction that was absorbing the energy from the surroundings. And so how is it that we know? Well, reaction 1, temperature decreased, so energy was taken from the surroundings and absorbed by the system. Reaction 2's temperature increased. So energy was released from the system to the surroundings. Now, I know I've got a typo there, but I'm sure you can fix it on yours. Okay, here we go. Next one. Observe the graphs below. Which graph matches with reaction 1 and which one matches with reaction 2? So if you have molecules, if you have a system that is giving off energy, what's going to happen to the amount of energy that the products have? Well, if energy is being given off, that means that the products are going to have less energy. And that is what we have here in graph A. Our products, the energy of our products is less than the energy of our reactants, which means that energy was released. And so our reaction that was releasing energy was actually reaction 2. So reaction 2 would match with graph A. In graph B, the energy of our products is greater than the energy of our reactants. And I can tell because my products are higher. They're at a higher amount of energy than my reactants are. So what this means is that my reactants absorbed some energy, making the products have a higher amount of energy than the reactants from where they started. So reaction 1 would match with graph B. So number 3 says one of the observed reactions is known as exothermic and the other is endothermic. We need to figure out which graph is which. Well, remember that an exothermic reaction means that energy is being released. Where is energy being released? Right here in graph A. So graph A is an exothermic reaction. Which graph is endothermic? Well, that would be graph B. And the reason why is because an endothermic reaction is going to have its system absorbing heat from the surroundings so that the products have more energy than the reactants that they started from. So letter B is endothermic, where the energy is going indoors or into those molecules. Okay, so if I want to explain my choices, I'm going to pause this and then I'll show you what my answer is. All right, here's my answer. So graph A is exothermic because the system, the molecules, are releasing energy into the surroundings, and that makes the products less energetic than the reactants. And that's what we have here. My products in graph A are of less energy than the reactants. In graph B, we have our reactants taking in energy from the surroundings, making our products more energetic than the reactants. So my products should be higher on the graph, which they are, than, so here are my products higher than the reactants are. Okay, if you haven't watched that whole video with the toothpick, then you can go back and watch it. All I'm doing is breaking a toothpick. But my point is that I had to add energy. So my fingers had to add energy to the toothpick in order to cause it to break. And so I had to add energy to break it. All right, number 5 says, write and balance the reaction for the combustion of methane. Methane is CH4. So I'm going to pause this and write down my answer. All right, here I am again. And as you should recall from our last unit, whenever you have combustion, you have a hydrocarbon, which in this case is methane, CH4. We're adding oxygen to it, and our products are carbon dioxide and water. And then I added my coefficients to that. So go ahead and put this on pause and watch the next video, Breaking Bonds in Molecules, and then come on back. Okay, so did breaking the chemical bonds require the input of energy or the release of energy? Well, just like the toothpick, it requires an input of energy. I gave you even a little clue in that video too, that I was adding energy in order to take apart all of those molecules. All right, so consider for a minute, if the breaking of chemical bonds requires the input of energy, then the forming of chemical bonds is going to do the opposite. In order to form bonds, we need to release some energy. So breaking is opposite forming, and input is the opposite of release. So they're just opposites here. So the breaking of chemical bonds requires energy to be added, while the formation of chemical bonds is going to cause the release of energy. Okay, so letter A says, use your graph to justify your choices. I've given them to you again. You just need to label them as endothermic or exothermic. So right now we're just labeling these as endo or exo. As I said before, letter A is exo and letter B is endo. Okay. So what I'm saying is that energy has to be put in. So here is my line for energy going in on both sides. So here, that's where we have the breaking of bonds. So breaking bonds, energy in, breaking bonds, energy in. But I've also got another line, my downward slope right over here. Here's my green line. So here we have energy out, forming bonds. And over on this side, I have energy out, forming. Okay, sorry about that. So we were talking about this green line here on the opposite side of the blue line. And here we've got energy out in order to allow new bonds to form. Because remember, a chemical equation is or a chemical reaction happens when bonds are broken. That requires the input of energy. And then atoms are rearranged. And then they're bonded together in a different order. And so in order to form those new bonds, to make those products, some energy is going to have to be released. How much energy is released is what determines whether a reaction is exothermic or endothermic. If more energy is released during the formation of bonds than the amount of energy that went in, we have an exothermic reaction. If less energy goes out to form the bonds than the amount of energy that was added to break them, then we have an endothermic reaction. Because where did the rest of this energy go? Well, it's in the bonds. So it's in the system. So that's what this all means. Okay, now let's take a look at number 7. Whether a reaction is endothermic or exothermic depends on how much energy is added to break reactant molecule bonds compared to how much energy is released upon the formation of new product molecule bonds. So below each graph, which I gave to you down here, you need to write the statement that best matches it. So in which graph does energy added to break bonds, is that greater than the energy out to form bonds? So let's draw our lines again. So here in our, remember this is exo and this is endo. And here is in exothermic, the line to break bonds. Here it is in endo. And here is the line to reform the bonds. Reform the bonds. So in which graph is the green line shorter? Because that's what this equation is saying. In which one is the energy added to break bonds greater than the energy out to form bonds? Well, that would be endothermic. So this statement goes to this graph. My blue line is longer than my green line. Energy added is greater than energy released, which means then that my other statement describes exothermic. The amount of energy added, my blue line, is shorter than the amount of energy released to form the bonds. And so this line, my green line, my energy outline, is longer. Okay, I'm going to pause this and show you my answer. So as I was writing my answer, I thought, maybe I should say this in a little bit of a different way. So I've already explained about the lines, but let's take a look at the energy of the reactants and the products. So in my exothermic graph, which is graph A, you can see that my products are lower than my reactants. In order for that to happen, more energy must be released to form product bonds than the amount of energy that was added to break reactant bonds. On the endothermic side, my products have more energy, they're higher on the graph than the reactants are. So the amount of energy released to form the product bonds must have been less than the amount of energy that was added to break the reactant bonds. So that was just another way to say that. Okay, I'm going to stop this video here and then I will start recording the rest of this activity. So I'll see you back again in a little bit. Bye.